Hello and welcome back to PC Retro Programmer. In this series of videos we're going to be covering CGA Graphics Programming. We'll look at drawing lines, circles and ellipses, possibly splines. Then we'll cover things like animation and sprites, 3D rotation and very simple shading. Before we can start all of that though, we need to cover the bare basics of CGA, and fortunately it's really straightforward. In CGA Graphics, all you really need to do is change into a CGA mode, which is dead easy, and then start drawing dots on the screen, which you do by updating the relevant bytes of data in video RAM. And you can actually write directly to the video RAM on CGA. It's a really simple system and perfect for beginners to learn how to do graphics programming. So the place we should start is the actual layout of CGA memory. The first CGA mode that I want to talk about is mode 4, and this is a 320 by 200 pixel mode with 4 colors. Actually it's 3 colors plus a background color, but I'll get back to that in a moment. So this is the main graphics mode that was used by CGA games. You remember the ones with the really gaudy colors. There are actually 2 palettes that you could use in this mode. There was palette 0, which had the background color, and then it had green, red and yellow. And then there was palette 1, which had the background color, and then it had cyan, magenta and white. And there was actually also a mode 5. It gave you a third palette, and it had cyan, red and white. And then for each palette that I just mentioned, there is a high intensity and a low intensity version. And I think yellow becomes a kind of brownish color, and maybe white becomes a gray and so on. So the colors change a little bit when you go to low intensity versions. I'll talk a little bit later about how to set the intensities in palettes. And as I mentioned, one of the 4 colors is the background color, which for most games was just black. You would just have a screen background color of black. But it was actually possible to change this, and you can actually change it to any one of 16 colors. It's the same background color for the whole screen, of course, and I'll talk about how to set that a little bit later as well. For now, we'll just think of the background color as being black. Now I want to talk about the layout of the pixels in video memory. So first of all, there are 320 pixels across the screen, and we typically number these 0 through 319. And I guess it's just common on computers to start numbering at 0 instead of starting at 1. And the only reason I can actually think of for this is because that's how memory addresses work. You want to use all the possible values for memory addresses, so you have to use the value 0, so you might as well start numbering addresses at 0. And so that just flowed over into a whole lot of other areas of computing, and now almost everything is counted starting at 0. So in the x-axis, the horizontal axis, the pixels are numbered 0 through 319. The y-axis actually goes down the screen, so this is the opposite convention to mathematics, which would have the y-axis going up. So you have to be a little bit careful about that. The pixels are numbered going down from 0 down to 199. And so there are actually 80 bytes per line in video memory. Now the reason for that is because each byte contains 4 pixels. So these first 4 pixels here, 0, 1, 2 and 3, would all be in the 1 byte. There's a little diagram down here of how this works. So there's your 8 bits in a byte, and there are 4 pixels within the byte, so 2 bits per pixel. So if you work it out, 80 bytes per line with 4 pixels per byte gives you a total of 320 pixels across. Now the CGA memory starts at segment B800 in memory. There's 16 kilobytes of CGA memory, but it's arranged in a really odd way. So the first 8 kilobytes of CGA memory contain the even lines. So by that I mean lines 0, 2, 4, all the way up to 198. And the second 8 kilobytes, starting at offset 2000 in hex, contain all the odd lines, so lines 1, 3, 5, up to 199. Now, as far as I know, the reason for this is that the chip they used to implement the CGA card can only count as far as 127 in terms of lines, and so it didn't really make sense to have a screen mode with 200 lines if the chip can only count to 127 as a maximum value. And so they decided to break it into two lots of 100. So there's 100 even lines and 100 odd lines. But if you're any good at maths, you've already noticed that something doesn't quite add up here. 100 even lines at 80 bytes each would only give 8,000 bytes, and 2000 in hexadecimal is actually 8,192. And not 8,000. So there's actually 192 extra bytes left over at the end of the even bank and another 192 bytes left over at the end of the odd bank. And these just aren't used. You can put whatever data in them you like. Of course, it's not fast memory. Video memory is much slower than main memory typically. So it's not particularly useful, but in any event you can use these 192 bytes just as extra storage. So let's take a look now at how the pixels are laid out in the byte a little bit more closely. So as I said, 4 pixels here would be these 4 pixels in a byte, and that would be at offset 0. The next 4 pixels, 4, 5, 6 and 7 would be at offset 1, and so on. So within the byte you have 8 bits, and we typically number these from 0 to 7, starting with 0 at the right hand side. And this is just because of the way binary numbers work. So if you put a binary 1 in bit 0, that corresponds to the decimal value 1. If you put a 1 in binary bit 1, then that corresponds to a decimal value of 2, and then 4, 8, 16, 32, 64, 128. So this is the direction that we would normally write numbers. The further you go to the left in a number, the bigger the place corresponds to. But the pixels are in the other order. You actually have the pixel 0 within the byte at the top of the byte, so bits 7 and 6. And so there are actually 2 bits per pixel, and that means that there are 4 possible values for each pixel. There's 0, 1, 2 and 3. These are binary values, of course, 0, 0, 0, 1, 1, 0 and 1, 1. But they correspond to the decimal values 0, 1, 2 and 3. And these are the colors of the pixels. So this particular pixel, pixel 0, would have the color specified by those 2 bits in binary, 0, 1, 2 or 3. And the colors correspond to 0 for the background color, whatever that happens to be. As I said, the background color for the screen can be any one of 16 colors, but whatever that is, that's what it corresponds to. And color 1 in the palette 0, for example, would be green, then you'd have red, and then yellow. That would be palette 0, and so on. So that's how the pixels are laid out in bytes, how the bytes are laid out in lines, and how the lines are laid out in video memory. So in order to set a pixel on a screen, to draw a pixel, you just choose the color you want, you put the bits you want at the right position in the byte, put that byte into video memory. Of course, you have to make sure that you didn't modify any of the other bits, and we'll look at how to do that a little bit later. And then you put the byte into video memory at the right location, depending on what line you want, whether it's an even line or an odd line. And that's all there is to it. It's a very, very simple method of drawing pixels. So what we need to do now is to write some assembly language code for actually changing into a CGA mode 4, and then actually go through some examples of drawing some pixels on the screen. And then a little bit later, we want to write a little routine for drawing a pixel on the screen. And it'll just take a color and a coordinates set, an X and a Y coordinate, and it'll just set that pixel to the color that we specify. The first example that I have is just a very straightforward one, and I've called that point1.asm. And what this is going to do is just draw 2 pixels on the screen in the upper left corner of the screen. So very straightforward. So the code starts here, and the first thing we're going to do is set up our CGA segment. So you remember that the video RAM is at segment address B800 in hexadecimal. So we need to move that into one of our segment registers. And it's pretty typical to use the ES register for this, because then we can use the STOSB assembly language instruction for moving bytes into that segment. We just need to put the offset into DI, and then we'll be able to do that. So obviously we can't put that segment value directly in the ES register. It has to go via a general purpose register, and so there's actually 2 lines to set up our ES value. But that sets up our CGA segment, and the next thing we're going to do is change into the video mode. So our CGA mode, which is mode 4. And for this we're going to use the video BIOS interrupt 10H, and we'll use function 0, which is set video mode. So for that we need to put the function number 0 into the AH register, and we need to put the actual video mode into the AL register. So of course we can set both of those at the same time just by setting AX. So we'll put 4 into AX, and that'll set AH to 0 at the same time as AL to 4. And then we want to set up our offset, and again we want to use DI here because then we can use our STOSB instruction. And I've decided that I want the 2 pixels that I'm going to draw to be in the upper left corner of the screen in the same byte of video memory. So that's got offset 0, of course, so I just need 0 in the DI register, and we get that just by XORing it with itself. So now we're all ready to actually put some data into video memory at that segment and offset. And of course the instruction we'll use for that is STOSB. It'll just move whatever's in the AL register into segment given by ES and offset given by DI. So what value are we going to move in? Well, I decided to use the value 81 in hexadecimal. So if you write that out in binary, 8 is 1000 and 1 is 0001 in binary. So this is what it looks like. And the first 2 bits of that are 10, which is going to be color 2. And by default, when you change into the video mode 4 using the BIOS, it'll blank the screen, and it'll also make the palette number 1. And so this color 2 here will actually correspond to the magenta color. Then we're going to have a background color because we have color 0, and the background hasn't been changed by us, so it'll be black. So that'll be a black pixel. Then we'll have another black pixel, and then finally color 1, which is the cyan color in palette 1. So we should get magenta, black, black, and then cyan in the upper left corner of the screen, those 4 pixels. And then the rest of the screen should just be blank because the video mode 4, when we changed into that, the BIOS will have cleared that for us. So we can look at that as long as we want until we have a key press. So just going to wait for key press here using interrupt 16H, and function 0 is wait for key press. And then we'll change back into the ordinary text mode, getting ready to finish the program here. And normally the text mode we want is mode 3, and so again we just use function 0 of the BIOS video interrupt 10H, And that'll get us back into mode 3, the text mode. And finally we can exit to DOS. That's the end of our program. So let's assemble this and see what actually happens when we run it. So as usual, it's just tasm.1, and then we have to link it, of course, and we should be able to run it. So, and there you have it. We have a magenta, black, black, and cyan in the upper left corner of the screen. So that's our first example. Before we move on, let's make a few changes to our program. The first thing I want to do is change the palette that we're using, and as I explained, one way to do that is to use video mode 5 instead of 4. And this uses the undocumented palette, the one that IBM didn't document, and it gives you cyan red and white instead of cyan magenta and white. So the other thing that I want to do is to set the background color, and I'm going to set that to a 1. And the way this is done is to move OBH into the AH register, and that's actually used for both setting the background color and for setting the palette between the CGA palettes 0 and 1. So in order to select between the two, we actually need to put either 0 or 1 in the BH register. So if we put 0 in the BH register, this is the set background color function. So let's move into BH 0. But we also need to put the actual background color in the BL register, and we want that to be 1. So we may as well just do move into BX1. And then it's just the ordinary int 10H for the video bias interrupt. So let's just assemble that and see how it actually looks. So we'll link it. And now it should have a different background color, and there should be different colored pixels than we had before. So as you can see, we now have a blue background. It's a little bit hard to see, but that first pixel should be a red pixel now instead of a magenta pixel, but otherwise everything's the same. So that takes care of those. Well, what about the other palette, palette 0 of the CGA? As I explained, in order to set the CGA palette, basically we do exactly the same as what we just did, but instead of using subfunction 0 of the function OBH, we use subfunction 1. So what that means is that we want a 1 in the BH register now, and the palette that we want, which is 0, we want that in the BL register. So basically what we want now is 0100H in the BX register. And we're not setting the background color anymore, we're setting the palette to 0. Now it doesn't really matter if we use mode 5 or 4 here, because in mode 5 we have red in the second color, but we already have red in the second color with this palette, so it makes no difference whether we use mode 4 or 5 for this one. So we might as well just go back to mode 4. So let's save that, and then we'll assemble this and link it. Now this also won't work on all systems, and it's actually a bit hard for me to tell whether that's a green pixel or not. I'm not sure if this CGA implementation actually supports that. But in theory that should be a red and a green pixel instead of a red and a cyan. So that's the palette 0, the first palette of the CGA card. Now the final thing that we want to do is to write a function for drawing pixels on the screen. And so I've written a piece of code here in point2.asm which draws a pixel at a given location. So you give it a coordinate pair x and y, and you tell it a color to draw the pixel, 0, 1, 2 or 3. And so this function is called CGA point. So it's a little bit similar to the code that we just wrote. It first sets up the CGA segment, but we need to do a bit more work for the offset now because it could be any pixel on the screen. It's not necessarily in the first byte of video memory. So the first thing that we have to do is check whether we have an odd or an even line. Remember that all the even lines are in the first bank of video memory and all the odd lines are in the second bank, the odd bank. So basically if y is odd, we need to add 8192 to the offset. Now I'm actually just using a little trick here, which I discovered when making the videos for this channel, that you can compute the offset times 4 much more efficiently than you can compute the offset itself. And then right at the very end, divide by 4. And this still works out cheaper than computing the offset directly. So this is what I'm doing here. Everything will be multiplied through by 4 initially. So first of all, we set the offset to 0, and then we load up the y value, and then we divide it by 2. And the carry flag will get set if it's an odd line. And so this single line of code here actually adds 4 times 8192 to the offset. So really efficient. So now we have y divided by 2, and this is precisely the value that we need in the next part of the computation. We need to compute 80, because there are 80 bytes per line, times the number of lines in the bank that we're dealing with. So we're either in the odd or even bank here. And of course we're only counting even lines or odd lines now, so we only need half of the lines, and so this is y on 2. So we'll end up with 80 times y on 2, and that'll be the offset within the bank. And of course everything's multiplied by 4, as I explained. So this is what this piece of code does. It just takes the value y0 on 2, which is already in the AX register, and then it does some computations to compute that 4 times 80 times y on 2, and then it adds it to the offset di. Alright, so then the next thing we need to do is deal with the x part of the offset, and normally we'd have to divide the x part by 4 because there are 4 pixels per byte. But remember, we're computing the offset times 4, so if you divide by 4 and then multiply by 4, you just get the x value. So we really just add the x value to the offset. And then the other thing that we're going to need is which pixel within the byte we have. So this is either going to be pixel 0, 1, 2 or 3 within the byte, and we get that by ANDing that x value with 3. So this will give us a value of 0, 1, 2 or 3 depending on which pixel we have in the byte, and we'll deal with this value in a moment. The final thing we need to do for the offset is just to divide it by 4, and so that's what these two lines do. So now we've completely computed the offset. So the reason we needed that x mod 4, that value 0, 1, 2 or 3, is to compute our color and mask bytes. So basically the way drawing pixels works is you read the pixel information from video RAM. You basically read the whole byte at the relevant offset, and then you AND it with some mask. And this mask will have 1s in all the bits that you're not interested in, but it'll have 0s in the 2 bits that you are interested in. And the reason that you do that is you want to clear out those bits so you can write in whatever value you want in there. And so once you've cleared those out using an AND, then you do an OR with the color information that you want to put into those bits. And so that's the second part of the computation. So there's an AND and an OR, and then you just write the byte back into video RAM, and so that will only change the pixel you're interested in. It won't touch any of the other 3 surrounding pixels in that byte. So this is what the code looks like. We just move the color that we want into the AH register, and we move a mask into the AL register, but we're going to need to shift both of these into the right place, and that's why we need to know whether we're dealing with pixel 0, 1, 2, or 3 within the byte. So that's what's in the CL register at the moment. We computed that above here. But the amount of shifting that we need is actually twice that value. So we actually need to shift by 0 bits, 2 bits, 4 bits, or 6 bits, not 0, 1, 2, or 3. So we actually need to multiply that value in CL by 2. So that's what this line is for. And then we actually just rotate our mask and our color bytes into the right place. So that's what these lines do here. So now we have a color and a mask that we can use for displaying a pixel on the screen. And here's the actual code that we use to change that pixel. So the first thing you do is you get the pixel from ESDI in video memory. So that's the byte that's there already. And then you AND that with the mask, which is in AL. So that will just zero out the 2 bits that we're interested in. And then we OR that with the color information, which is in the AH register. That's also been shifted into the right place. So it will now put the color 0, 1, 2, or 3 into those 2 bits that we're interested in that we've just zeroed out. And then once we've done all that, then we just write the byte back into video memory. And we can just do that with an STOSB instruction. We haven't modified DI or anything at this point, so we're still pointing at the right location in video memory. And so that writes the pixel back into video memory. So that's really all there is to it. We just pop the registers that we saved and return from our function. And finally, I've got a little program here to draw a whole bunch of pixels on the screen. So first of all, it's going to change into the CGA mode 4. And I'm going to draw 200 pixels on the screen. And so I put a value of 199 into the SI register, which I'll use as a count. I'm using a register here that I didn't modify inside my pixel drawing routine, so that I don't need to save it or anything. And so basically, I start at 199, I'm going to go all the way down to 0. And so what I'm going to do is draw the pixels at coordinates 199, 199, then at 198, 198, then 197, 197, and so on, all the way down to 0, 0. So basically, this line here is just to set the color. So I want color 1 for my line. That's what I chose to use. And here's where I call our point drawing function. And remember, the arguments to functions get pushed in reverse order. So first of all, the color gets pushed. That's in AL, so we have to push AX. And then we just push the coordinates that we want, and that's just the value in SI twice. We're going to use the same coordinate for X and Y. And once we return from our function, we just need to readjust our stack pointer again. So we had 3 pushes, which is a total of 6 bytes, so we need to add 6 bytes back onto the stack pointer. So that draws 1 pixel on the screen, and then I'll just decrement SI. So it'll just count down from 199 to 0, and I actually want to draw the pixel at 0, 0, so I actually want to loop until the value is negative, and so I just use jump if no sign, and that will keep looping until I end up with a negative value in SI, then it'll stop. So finally, I just wait for a key press, restore the video mode, and quit, just like we did in our previous program. Alright, so let's save this, and then we'll assemble that, and we should be able to see a line being drawn on the screen. So let's link that. And this should draw pixels in a diagonal going from 199, 199 all the way down to 0, 0. So let's run that, and there we have it, a line in color 1. So obviously this is a really slow way of drawing a line because we've got a lot of overhead in that function for drawing a pixel. All that computation to work out the offset and the various other bits and pieces. We're computing a color and mask byte for every single pixel we're drawing. It's very, very expensive, and of course we're pushing and popping registers when we call the function and so on. So this is really not particularly useful for anything except writing really simple code. So don't think of this point drawing function as something that you're actually going to use in practice. So some of the other videos on the channel in this series are about drawing lines and circles without using a pixel drawing function. So pixel drawing functions can be useful for some things. For example, you could do a star field. Even those don't get done using a pixel drawing function by people in the demo scene, for example. There are lots of other ways of doing it that are much faster. But there are some things that you can do if you have a pixel draw function. But the main objective here was just to introduce how to use CGA memory, the palettes, and obviously the background color and so on. So that's all of the real basics of using CGA.